There are two methods to balance redox equations: the oxidation number method and the half reaction method, also known as the ion-electron method. The oxidation number method is based on the change in the oxidation number of the reducing and oxidizing agent. The half reaction method is based on splitting the redox reaction into two halves, the oxidation half and the reduction half. Let's discuss the various steps to balance the redox equation using the oxidation number method with the help of an example. In this reaction, permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. In the first step, write down the correct formula of all the reactants and products in the reaction. The second step involves assigning the oxidation numbers to all the elements in the reaction and also identifying the atoms which undergo change in the oxidation number. We know that in polyatomic ions, the sum of the oxidation numbers of all atoms in the ion is equal to the charge on the ion. Thus, the oxidation number of manganese in permanganate ion may be calculated as follows. Let the oxidation number of manganese be X. We know that the oxidation number of oxygen is -2. Hence, X plus 4 multiplied by -2 equals -1. Therefore, X equals to +7. Thus, the oxidation number of manganese is +7. We also know that the oxidation number of a monoatomic ion is same as the charge on the ion. So, in the case of bromide ion, the oxidation number will be -1. Now let us focus on the products. First, we'll calculate the oxidation number of manganese in manganese dioxide. We put the oxidation number of manganese as X. X plus 2 multiplied by -2 is 0. So, X plus -4 is 0. Hence, X equals +4. Next, we'll calculate the oxidation number of bromine in bromate ion. Let us consider the oxidation number of bromine in bromate ion as X. X plus 3 multiplied by -2 is equal to -1. Thus, X is equal to +5. Now, observe the change in the oxidation number of the elements. The oxidation number of manganese changes from +7 to +4, and the oxidation number of bromine changes from -1 to +5. Note that oxygen does not undergo any change in oxidation number. In the third step, calculate the total increase or decrease in oxidation number per atom and for the entire molecule or ion in which it occurs. If the increase or decrease in oxidation number is not the same, then equalize them by multiplying with suitable coefficients. In this case, the decrease in oxidation number of manganese is 3. While the increase in oxidation number of bromine is 6. Hence, to make the decrease equal to the increase, we multiply the decrease in oxidation number, that is, 3 with 2. Which means that we introduce a coefficient of 2 with manganese on the left and the right-hand side of the equation. Now, let's come to the fourth step. Identify the involvement of ions and balance the ionic charges. If the reaction takes place in water, then add H plus or OH minus ions on the appropriate side, so that the total ionic charge of reactants and products is equal. If the reaction takes place in an acidic solution, then add H plus ions. If the reaction takes place in a basic solution, then add OH minus ions. As the reaction occurs in the basic medium and the ionic charges are not equal on both sides, we need to add 2 OH minus ions to the right side of the equation, so that the ionic charges are balanced. Finally, balance the number of hydrogen atoms. This can be done by adding H2O molecules to the reactants or products as applicable. In this case, we have 2 hydrogen atoms on the right-hand side and no hydrogen atoms on the left-hand side. Hence, add 1 water molecule on the left-hand side to balance the hydrogen atoms. Now, also check the oxygen atoms. If the numbers of oxygen atoms on the reactant and product side are same, then we can say that the equation represents a balanced redox reaction. In this case, if we count the number of oxygen atoms on either side of the reaction, we can see that there are 9 oxygen atoms present on either side. And thus, the equation represents a balanced redox reaction. The half reaction method is based on the principle that electrons lost during the oxidation half reaction are equal to the electrons gained during the reduction half reaction. Let's look at an example. In this reaction, dichromate ions in aqueous acidic medium reacts with ferrous ions to give ferric and chromium 3 ions. Let's look at the steps involved. First, write the skeletal equation for the reaction in the ionic form. Then identify the species which have been oxidized and reduced, and split the reaction into 2 half reactions. This is step 2. In this case, the oxidation number of chromium decreases from +6 to +3. Thus, dichromate ion is reduced. Simultaneously, the oxidation number of iron increases from +2 to +3. Thus, iron is oxidized. Thus, the 2 half reactions can be written to show the oxidation half reaction and the reduction half reaction. In the third step, balance all atoms except oxygen and hydrogen. In this example, the oxidation half reaction is already balanced since the numbers of iron atoms are equal on either side of the equation. In the reduction half reaction, there are 2 chromium atoms on the left-hand side and only 1 on the right-hand side. So, we'll multiply Cr3 plus by 2 to get 2 chromium atoms on the right side too. Now in the fourth step, balance the H and O atoms. If the reaction takes place in an acidic medium, add H2O to balance O atoms and H plus to balance H atoms. If the reaction takes place in a basic medium, add H2O to balance oxygen atoms and OH minus ions to balance hydrogen atoms. In this case, in the oxidation half, there are neither oxygen nor hydrogen atoms. But in the reduction half, you can see that there are 7 oxygen atoms on the left-hand side, but no oxygen atom on the right-hand side. As the reaction occurs in acidic medium, to balance 7 oxygen atoms on left-hand side, we add 7 H2O molecules on the right-hand side. Now, after the addition of 7 water molecules, there are 14 hydrogen atoms on the right-hand side, but no hydrogen atom on the left-hand side. Hence, to balance the hydrogen atoms, we add 14 H plus ions on the left-hand side. In the 5th step, balance the charge by adding electrons to one side of the each half reaction. If required, make the number of electrons equal in the 2 half reactions by multiplying one or both half reactions by appropriate coefficients. The charge of iron on the right-hand side is +3, while on the left-hand side it is +2. Therefore, to balance the charge, we will add 1 electron to the right-hand side. In the reduction half reaction, there are net 12 positive charges on the left-hand side and only 6 positive charges on the right-hand side. Hence, to balance the charge, we add 6 electrons on the left-hand side. To balance the electrons lost in the oxidation half and gained in the reduction half, we multiply the oxidation half by 6. In the 6th step, add the 2 half equations to obtain the overall reaction and cancel the electrons on each side. Thus, we obtain the net ionic equation as shown. Finally, verify the equation by ascertaining that the same type and same number of atoms and charges exist on both sides of the equation. Since the charges on both sides are equal, this is a balanced redox equation.